Okay, I'm recording right now. I want to tell you that, that I will try to end the lecture a little earlier because there is a meeting of the whole department. It was scheduled, at 4 p.m., which is, at 3 p.m., which is before our class ends. So try to end a little shorter so I can attend it. It's like with this setting where, we are all interacting just on Zoom. It's important to check in and understand what's going on, because you cannot, you tend not to talk to other people, as you noticed, through just bumping into them on a corridor. Okay, so I will start my presentation. I will. We finished last time with I'm saying that I was promising that a proof of a very nice property of Max, which is okay. So first of all, of information theoretic Mac, and then a practical Mac that comes out of it. Because I want to make this lecture a little shorter, so I will jump into the other material, and then if time remaining, I will do that one. I will fill up that one. It is on the slides that I posted last time, but if we have the time, I will go over it. Okay, so let me, okay. Oh no, I just, hold on. No, that's fine. Okay, let me start this one. Okay. Okay. So we looked at Macs and what they are, like how to construct them, and a related object in cryptography that we haven't yet introduced is called collision resistant hash. In particular, it can be used to implement a Mac, but together with a PRF, but it has many other usages. Okay, so okay, so we have seen this ECBC, NMAC, the nested MAC, the parallel MAC, and the last few slides, which I didn't go over, is it's called Carter-Wegman MAC. It came from the information theoretic MAC, and just a single instance of a PRF. So okay, so we skipped that one, but it's on the slides. And now we'll show. Okay, so a collision resistant hash can also implement a MAC. Okay, what is collision resistance? So it is an unkeyed function. So okay, PRGs were not keyed, but they had something that was like an equivalent of a key in some conceptual way. It was a secret seed, randomly chosen, and a PRG input is that secret randomly chosen seed, and it uses to generate. So that's how a PRG is used in a stream cipher, right? The key is the seed. Hash function has no natural sequence. It's a function from a message space to some target space, where it makes sense if the message space is larger than the target space. And now, whenever you have such a function, it's a deterministic function, right? I mean, a function is a deterministic function. Whenever you have a function from a domain that is larger than the counter domain, then it must have collisions. And a collision is a pair of three images, which are different, but the function maps them to the same image, right? And if the domain is larger than the range, then this is necessary. They must exist, right? By a, whatever, that argument, pigeonhole principle. Okay. So we say, nevertheless, that a function like this is collision resistant if for all efficient algorithms, it is the case that the probability that this algorithm finds such pre-image that creates a collision is negligible. So now the collision resistance game is that, okay, so now it becomes slightly more complex because there is no randomness. The challenge, in all our previous games, we said, okay, the challenger picks what was the game with the PRG? The challenger picked a random seed and created either PRG on this random string or completely random string and asked the adversary, distinguish between these two. Adversary cannot, okay? But the probability goes with non-negligible advantage, but the probability goes over random seeds that create this PRG string or completely random strings in the other case. In PRF, what was the randomness? It was the choice of the key. And then box is created, either as a PRF on a random key or as a completely random function, gives that to the challenge, adversary queries them, inputs, outputs, and says, I cannot tell between the two. The probability in this in the experiment goes over the random secret inputs of the challenger. Keys, seed in the PRG case, key in the PRF case. For all our encryption examples, key, right? Plus in a randomized encryption, there's also randomness of the, in encryption also that was public. So in all our cases of randomized encryption, the randomness was the IV, which was part of the ciphertext. In a MAC game, message authentication code game, right? The challenger picks the MAC key, keeps it secret, and adversary gives messages, gets back MACs, gets messages, gets back MACs. Here it needs to forge. But the probability goes over the random choice of the key. Here, there is no random choice. Adversary gets the function, description. This is circuit that encodes this function, algorithm, however you want to describe, because for a hash function to be useful, it must have succinct and description, and it must have a polynomial time algorithm that computes it, right? So think of H as a description of that algorithm. Adversary sees it, and there is no randomness. So if you, this probability, what does it go over? Well, randomness of adversary, but note, look, if I say for all efficient algorithms, and these messages exist, so no hash function can be secure against this, because imagine this M0 and M1, the moment M is greater than T, then M0 and M1 exist to satisfy this. So think of them, and how big are they? How complicated are they? Well, they have as many bits as the message space. So clearly they are linear in the description of this hash function, right? So there is an efficient algorithm that has these M0 and M1 built into it. And it just outputs those. And boom, it has a collision. So efficient algorithms like that exist. But it's a kind of a funny quantifier. They exist on paper. I mean, in theory. But now give it to me. So tell me that algorithm. And we don't know, because so some, there is hash functions which are not broken in the sense that, okay, these algorithms exist, but we don't know them. Nobody knows a single example of this M0 and M1, nor do they know how to efficiently compute these M0 and M1. So this is, from a complexity point of view, something fishy is happening here. And basically, we eliminate this fishiness by pretending that the probability goes over the randomness in the choice of creating this hash function. So in other words, we say, okay, this hash function is not fixed. It is randomly generated from some inherent space. There was a, like, think of S boxes inside des. So think of the des algorithm with empty S boxes as the algorithm, and then the choice of S boxes as the randomness that created a particular instance of des. But that's the same in a hash function. Okay, so and now if hash function description really was created in this fashion, then these models, this can plausibly model reality. And the reality in that way is modeled like this. So somewhere, the committee that decided on the hash functions, indeed, they are decided by multiple people basically analyzing the algorithms and all stamping that we think this one is resistant, and there is randomness in the process because part of the algorithm description has some basically keys effectively, and in this so you can think of this as a kind of a randomized process that creates a hash function description, and the adversary gets is the whole world, so to speak, combined computing capabilities of all the computers and all the algorithm designers and all the cryptographers and everybody, who are getting as input this hash function, and now are trying to jointly compute a single collision, and they can't. Okay, then you call that a collision resistant function, right? So of course, in practice, a design is proposed, and then maybe a few years later, somebody does break it, right? So that happened with SHA-1, for example. Okay, famously. So, okay. But and also in practice, these are not asymptotic things. There is a particular security parameter for which this function is designed, although there might be a family of functions. So SHA is SHA-256, and there's also SHA-512. Okay, and there was a SHA, and there was a smaller output. And okay, I forget whether MD5 has these similar extensions. Okay. Now, if you have a collision-resistant hash, you immediately get a MAC from a single PRF. Because, look, remember that using a PRF, we can implement a MAC on a short message, right? So a MAC on a short message is just a PRF applied to the message space. And that's already a MAC. Okay. So now, if I have a hash function that hashes any big message space onto the plain text space of this small MAC, the MAC on the small messages, short messages, so think PRF, like here, block cipher, then I can hash messages. I can now MAC messages in this big space, because in order to MAC them, I will apply the original MAC to the hash of the message. And in order to verify it, I will again hash the message and apply the original verification to the hash. Okay? Now, why is that secure? It's a simple argument, right? Because you basically have to consider two cases. So I'm going to argue that if you have an attack on this, then you must either break security of the small MAC, or you break collision resistance of H. Why? So let's say that you have an attack on this big thing. So you're sending some messages, you're getting MACs, which are these, and then you create a forgery. So there's two cases. that forgery is a message that has a different hash from all the previous ones. Well, in that case, you must have you already broke a security of the small MAC, because you were given MACs on some hashes and you created a valid MAC on a new hash, which is not equal to previous hashes. Okay, so you broke security of this small MAC. The other case is that the new message in the forgery has the same hash as some previous message, but then obviously you broke collision resistance of H, right? You found a new message which is different from some previous one, but its hash is the same. End of proof. Okay. So here is the MAC, for example. Take a SHA-256, meaning it's a hash function that takes arbitrary message and outputs a 256-bit string, and it's believed to be collision resistant. Okay. So now you need a MAC that takes 256, that MACs correctly 256 block strings. Well, you can just remember that the CBC MAC is secure if without the final post-processing. So the raw CBC MAC is secure if you run it on fixed block length. This case, from how big is the block of AES? 128. So this thing will have 2 AES blocks. So you need to do a CBC MAC on 2 blocks, right? That's what this is. And that's a PRF on 256-bit messages. You're done. Okay, very, very simple. Okay. Now, okay, so that actually guides through the security arguments that I was just sketching. You know, there is other usage to collision resistance. So, for example, now you can have a protected file system without a key, because let's say you hash all your files, and you don't have a key, but you do have small secure storage. So it's public, everybody can see it, but they cannot write into it. So it's a very different security property than a key that is used if you want to protect integrity of a file system using a MAC, right? You need to have a private key, and if somebody steals this private key, then well, they can MAC modified files, and you are messed up. Okay, so but here you don't need secrecy of these hashes. What you need is that somehow this is a read-only. So okay, I don't know, a CD drive, a read-only CD drive, right? So if there is a read-only public data structure like this, you can, for example, check that you were given a correct file because you can locally hash it and compare to these values. Well, you still need authenticity of these values, but that's another issue. Okay. Hash functions have the following generic attack. If whatever the range is, the following generic algorithm finds the range. So let's say that the range has n bits. So a range is n bit strings. The generic algorithm can find collisions in time that is 2 to the n over 2. So if this thing is 160, this thing is 80, right? If this thing is 64, then this thing is 32. Okay, in other words, if your hash has 64 bits of outputs, that's not very good, because in a time 2 to the 32, which is completely reasonable, I can find collisions against it. And how? Well, I just take this many random samples, or even let's say random samples from the message space. I hash them, and I should expect a collision. Why should I expect a collision? Because let's say H is has a very uniform distribution. So on random inputs, it basically creates random outputs. Then every time I pick an input at random, I sample from the output space at random. So therefore I get collision with this bound by per se probability. Now think that, okay, maybe H doesn't have this uniform output property. Maybe it skews. So if I sample on random inputs, it skews the distribution, and certain messages are more probable in the range, are more probable than others. That's even worse. Okay, the uniform distribution is the best case. Any other distribution of outputs of H on random inputs will even increase this probability only. Okay, so that's why so SHA-1, which I put in gray because there's a tax against it, was faster, could process messages with a faster speed, and this is, by the way, per megabyte of the input that you're hashing. But because its output was 160 bits, the generic attack is 2 to the half of this, so 2 to the 80. That's why if you upgrade security to the 128 bits, the hash function needs to have twice longer output. And that's why the hash function parameters is like you see here. And MD5 has 160-bit outputs, which corresponds to 80-bit security. Okay. Okay, but the attack against SHA-1 actually was much faster than this generic one. Okay, how are hash functions construct, right? Because it's like I had all these complicated constructions on max, on large input, and here it's like from a hash function you get an immediate one. So here is the Merkle-Damgard paradigm. So as usual in cryptography, we start with, I'm not going to give you a construction from scratch, but if let's say that we have a collision resistant function that can process short messages. Of course, it must process longer than its output, or otherwise it's trivial. An identity function is collision resistant, right? So let's say that it hashes on 260-bit strings, and its inputs are 320-bit strings. And I'll show you how to compile this into a general hash that can take arbitrarily long message. Okay, and then of course we'll see how to build this small guy. So here is the Merkle-Damgard compiler. It takes a small collision resistant hash function. These are called compression functions. A compression function is a collision CRH that works for fixed input size messages. Okay, and given that we obtain a big CRH, meaning the following. Let's think of the small compression function as taking a bit string that is represented as a pair of something in the target space of the hash and the rest. So simply speaking, if this is 160-bit strings, then here you have a 160-bit string. And okay, let's take like SHA-256. So this is 256 bits, this is 256 bits, and this, let's say, is another 256 bits. So this input here has 512 bits, and the output has 256. Okay, then how do I create the big hash? I take my message, I divide it into blocks which are as large as this bit size. So 256 in the case of SHA-256. I designated the size by X. Okay, the bit strings of that length, I designated them X here. So up to some limit, as usual, but this is polynomial time and can be set arbitrarily large. I mean, okay, you see based from security analysis how large, but essentially arbitrarily large. You can take any string that has up to that many blocks of this size, and now this construction gives you a collision resistant hash on the same target space. So 256 bits in the case of SHA-256. And so you divide your message into these blocks, and at the end you have some padding block. This padding block will encode the length of this message. Okay, it's also essential for security to do so. Okay, and the construction is like this. So the padding block, the last 64 bits encode the message length. So the total, you know, the largest number of L is 2 to the 64, which is plenty. And if there is anything remaining in the last block, then you pad it in a customary way. Okay. Let's call this. Let's denote these wires HI. So okay, how do you initialize this? There is some fixed IV, and it's part of the description of the instance of Merkle-Damgard. Okay, it's the fixed block. So this intermediary wire values, let's call them H0, H1, H2, etc. So the final hash is the last wire value, right? And notice that you can be done fast with a small hardware, so you only need this because then you just loop through this, right? By the way, this is inherently sequential. And here is the theorem about this of Merkle-Damgard, is that if the small collision function, the round function here, is collision resistant, then the whole big thing is collision resistant. My family is looking for something, but all right. And how do we prove it? By counterpositive. So in other words, if there is an attack on the collision resistance of this whole Merkle-Damgard construction, then the only way this would happen if that attack found collision resistance against the underlying collision compression function. Okay, and therefore, if the compression function was collision resistant, then so must the whole Merkle-Damgard construction. So let's see why that is true. So suppose that somebody found two big messages that Merkle-Damgard has the same output on. Okay, and basically, given such messages, it must construct at some point a collision against the compression function. So here is the circuitry. and assume for ease of okay. So look at the two messages represent two different values of these registers, and by the way, they can have different lengths. Okay, so let one of them have T blocks and the other R blocks. Okay, so the values here, the wire values, there are going to be HIs in one execution on message M, and when I put message M prime, I'm gonna call these values HI primes. The IV is the same in both cases, and by assumption, these two equal. So let's go from the back, that the output of this last compression on these two different sequences collides. So the output is the same. Well, if that is the case, then the little collision compression function, taking the one before last, HI, in the case I executed it on M, and that was this wire. And what was this wire? It was the last block of M followed by the padding block for that M. This compression function outputs the same output as the last compression function on the HR prime and the last block of the M prime message, right? Concatenated with the padding block for that one. And now there is two cases. If these inputs, so this whole string, this comma, don't be upset with the commas here. This is just because for our ease, it's easier to think of the inputs as a pair of this wire and this wire. But that's really just a concatenation of this and that. Okay, so this is a bit string. This is the left side of the bit string, and this is the right side of the bit string. That is all hashed by the compression function. And if this whole thing is different than this whole thing, then boom, I have a collision in a compression function little h. So I'm already done. I do have an attack on the little h. So the only other case is that this thing and this thing are the same. So in other words, the last block, okay, so what does that mean? First of all, the last block of the M message and the last block of the M prime message were the same, but also the padding blocks were the same. And now padding blocks include the input length. So therefore, the length of M and the length of M prime must have been the same. So therefore, T and R are equal. So therefore, this thing is the last block, are the two last, this is the last block of M and the last block of M prime, and they are the same. And okay, and now we recurse, because it also follows that this previous to last wire value was the same in both executions. Where the two executions are again, one execution, the orange stuff is M, the other execution, the orange stuff is M prime. And so this H3 value was the same in both executions. So we recurse the argument. Now let's look at the input to the compression function one before the last. And what do we now have? Again, two cases, because the output is the same in both executions, right? H3 in this case and H prime 3 is the same. So we have again two cases of these inputs. If they were different, then we have a collision in this compression function. And we're done. So the only other case is that these things were the same. but that means that the block before the last was the same in the two messages, and also this wire, intermediary wire value was the same. So continuing this argument, you will basically have two things. All these HIs from the last to the first must have been the same in both executions, and all the blocks were the same. If you didn't have this, the padding block didn't include length, then this argument would break in the last block. It wouldn't be clear that that it's necessarily true that M and M prime are the same. They have to have the same postfix, but when the other guy is shorter than, one of these messages is shorter, then the beginning of one message might be different. Okay, so there's other variants where this is not going to work, this reasoning, but it will work when you set it up this way. Okay, so, okay, great. From the minute you have, and by the way, this would work even if the input here was 1 bit larger than the output, right? So in other words, all you need is a minimal collision resistant hash function. So if you have a collision resistant hash function that given n plus 1 bit hashes it onto n, then you can now hash arbitrarily long messages. Just you would have to run a collision function a compression function per every bit of the message. So it wouldn't be particularly fast, but you can do it. Of course, for efficiency, you want to swallow a significant chunk of the bits of the message every time you run this, can be called a round function of this construction. Okay, so it's sort of a similar case as in PRG extension, and similarly as there, the question is, well, okay, how do I, the question for PRG, well, how do I stretch an n bit seed into an n plus 1 bit indistinguishable from random string? This we actually, by the way, tabled, and we said we're going to come back, time allowing, because it's actually a very beautiful and surprising result that you can do it. And we didn't say, okay, we said it can actually come from one-way functions, the same ones that we will see in public key crypto. Similarly here, okay, how can you get collision resistance even on, if you have to collide, if you want to hash just n plus 1 bit into n, okay, you are guaranteed collisions. You have to have collisions, right? Like on average, every image will have 2 pre-images if you reduce the bit size by 1 bit. But so collisions will exist. But how to construct that thing that is collision resistant? By the way, that does seem to be a very different kind of question. So whereas everything in the crypto world so far connected to one another, so from a minimal PRG, you get a maximal PRG, you get a PRF, you get a PRP using Feistels, you get an encryption, you get CPA encryption, you get max, everything you get from this tiny PRG. It just starts up the whole chain of reactions. Collision resistance, it's not known whether it relates to existence of a PRG, and how do you abridge between these two? There is no known relations. PRG also comes from one-way functions, So we can back this chain into yet even something more fundamental, a one-way function. And again, collision resistant function and a one-way function. Well, okay. So yes, there is an obvious relation. Collision resistance implies one-wayness. So a collision resistant is a stronger object, and because it implies one-wayness, therefore it implies a PRG and everything else. So I take back what I just said incorrectly, that there is no relation. Collision resistance could be the first guy in the whole block of dominoes. If you have that, you get everything else. Okay, so okay, how do you construct this? And okay, so how do you construct this little compression object? The object for the Merkle-Damgard, it is convenient to think of this object as split its inputs into a part that is the same size as the target and the rest. Okay. By the way, there is other collision resistance constructions than Merkle-Damgard. In particular, Merkle by himself showed that you can have a construction that is easier to parallelize, make it into a binary tree. So hash these two, and then these two, and then pairwise next, first level of binary trees. So now you have half as many blocks, and now recurse and hash the next two outputs on the next level, right? And create basically a binary tree, and the root is your final hash. Not only it is parallelizable, it is also has this nice incremental property that if you modify a single block, you can recompute the final hash faster. You don't have to recompute the whole thing. Basically, you can recompute along the path from that block to the root. This allows very nice data structures, like, for example, authenticated database, where you hash, well, and other, like, it's used in revocation lists. It's used, you can prove quickly that you modify, you make an amendment to some data structure, and you shortly prove that so, for example, everybody knows the MAC of some file system, and now a hash of a file system, and now I can modify one file, and I can recompute the Merkle tree and just publish small amount of data that allows everybody to recompute what the next target, what the next hash is. And it has multiple other uses, so it's a good data structure to know. Nevertheless, the small compression function is a part of everything. So how do I construct it? Here is a funny, surprising connection. Let's say you have a block cipher, and the Davis-Meyer construction of a compression function from a block cipher is like this. So the outputs are n-bit blocks, and I can take a key. So I parse my inputs. Anyway, so I have a pair, H and M, and the way I hash them is that I use the M part of the compression function input as the key. So the little m must be in this space, and I use the H part as the plain text in the cipher. I run the cipher on this, and I XOR the results with the H part. So here is the circuitry, where on the block cipher, I denote where the key goes with this little asterisk. So that's where the key, this MI will be interpreted as the key from the point of view of the block cipher here. So I drew it so that to mimic the Merkle-Damgard usage. Remember, so Davis-Meyer says that this whole block is a compression function. If in the context of a Merkle-Damgard compiler, the input here would be intermediate, in the so-called chaining variable, hi. The output will be hi plus 1. And this input will be the ith block of the message that you are hashing using Merkle-Damgard. So if this is a compression function you use, then the message, the block of the message that you're hashing in Merkle-Damgard will be the key. And the chaining variable will be the plain text. You will compute the cipher and then XOR the output with the chaining variable, and that will be your next one. Suppose that E is an ideal cipher. Okay, so remember, we use this notion arguing security of triple DES, arguing security of the DESX construction. So in other words, it's a collection of completely random permutations which are indexed by keys. So for every key, you get E instantiated with this key is indistinguishable from a random permutation. Okay, if you have only input-output ability to it, right? So you send some input to this box, there comes an output, and you can recompute it, you can run the box again, but you cannot tell the outputs. It's as if the box gave you random numbers. Okay, I mean, it was a random, implemented a random permutation. In that very strong model for what a block cipher is, you can show that finding collisions has it must take this many evaluations of E and D. Okay, that you cannot find collisions faster. This should be omega, actually not O. And this is the best possible because we already argued that look, the output space here is n bit long, so this is also the lower bound because this is also the upper bound because every if you have n bits, there's a generic attack that takes this long. What Davis-Meyer showed is that there is that's the best attack. That if this is an ideal cipher, there is no attacks that are faster. So let's look maybe at like a slight modification of this for a second to show that that would be broken, okay? So let's say that you try to simplify it like this. So you skip this postfix hash, okay? This output pad. So it's not collision resistant, so it's easy to build a collision. So HM and H prime M prime, which collide. How? Because E is invertible. So pick any HM and any M prime, and now invert it. So run E in the backward direction on M prime, where the output is this. Okay, so now you can check that if you apply E to this M prime key on this value, then you must get this input back, this plain text back, the ciphertext back, and therefore you have the collision. So a block cipher, because we're talking about running it on, here in this case, the message blocks will be keys. So of course you can manipulate message blocks, and in particular you can look at inversion of this algorithm, because this is a public algorithm. It's some encryption scheme, okay? And you can sample what it would output on a given MI, and you can compute it both forward and backward, right? Because the block cipher can be inverted given a key. But it doesn't help. So it breaks completely the simplified construction, but it doesn't help this one. I mean, intuitively, so you can compute it forward on some MI and HI, and you can compute it backward on MI prime. This gives you this wire. But now the hash of these equal values and this output XOR has to collide as well, right? So you have to correlate the back outputs so that the XOR, you will have a collision. If this is a random permutation, then computing it either forward on new places or backward on new places gives you random outputs, and so therefore this constraint is going to be hard to meet. Okay, this is just a sketch that this particular attack does not work. There is other combinations that are possible. So there is one called Whirlpool that, in addition to using H as an output body, it also uses M. And there is also sort of other forms of mixing where you take XOR of the two as your key instead of M. If you, of course, you can create like all sort of, many such variants, but some of them are insecure. And so detecting like what, if the block cipher is this perfect, okay, so so that's another insecure variant, but there's many others. So these things look deceptively simple, but their analysis might not be, and some of them might actually be, you can realize that they are broken. And are arriving with the lower bounds that say it cannot be broken, except for this lower bounds that matches the generic upper bound for attacks on a hash function. It might not be so easy. But so this is how SHA-256 is constructed. It's a SHA-256 is the Merkle-Damgard construction, because SHA-256 is not just, it can swallow any message of any arbitrary size. It is actually a Merkle-Damgard who runs Merkle-Damgard on particular compression function. That compression is made using Davis-Meyer construction from an underlying block cipher. That block cipher is really what a SHA designed. These two were already analyzed by other people and are sort of have been, beaten security. I mean, Merkle-Damgard, it's easy. And they are sort of understood as like clearly working and optimal. The whole thing is about the block cipher inside. And it's a particular block cipher, that is really heart of this SHA function. Because the output must be 256-bit blocks, so the block cipher works on 256-bit blocks, right? Because in a SHA-256, I want to hash eventually onto 256 bits. So the chaining variable is 256. So the blocks of this block cipher are 256. The key is how big of a message chunk can I consume. It's sort of the bigger this chunk, the better. But you know, you need this construction here to somehow emulate. I mean, you need to have some good basis to believe that this works like ideal cipher. So each change of even a single bit here instantiates another instance of a permutation that looks completely random and independent from any other key. That's why this cannot be too long, because how would you argue that any tiny change instantiates basically some permutation that is indistinguishable and independent? So there are strong requirements on what this block cipher should guarantee, and they are sort of non-standard, right? Because the standard notion of a PRF or a PRP, which is a standard notion of a block cipher security, considers its behavior on a random key. Inside of this Merkle-Damgard plus Davis-Meyer, this is not going to be a random key. This is going to be an arbitrary message, a block, 512 block of some message that is being hashed, which can be highly non-random, right? And in fact, adversary chooses these messages. He can search for them to find collisions in a hash function. It's a, you know, the design of this is a trade-off between complexity of this hardware and how big of a block I can swallow all at once. In particular, another thing that is special about these block ciphers is that you definitely don't want a design which is going to have very complicated way of assigning round function keys based on this one, because here is an instance of the block cipher that will be run every time on a new key, because each of these blocks, right, will be different when you process a big message. So it's a different design space, but yet it's sort of nice that it all comes down to similar things. There is a block cipher inside of a hash. It is not the only way to construct a hash, but yet every practical hash function has this structure. Okay, it has a block cipher inside. Let me. Sorry. Okay, I was just checking the time. Hold on. I got lost with I pressed the button and I got lost in the presentation. Hold on, let me check that I'm okay. Here is a hash function that I don't need. Well, I still need assumptions for, but it's a different hash function. It comes from public key crypto system, and for public key assumptions. Well, no, from the same assumptions that underlie public key crypto systems. Imagine that you have a prime, and you hash, and you have two numbers u and v, which mod p. Okay, and the way you hash is that you take, again, I break my hash message into left and right side. These are now the same sizes, H and M. They both are, sorry, this should be capital H. They're both numbers mod p. Okay, so yeah, so let's say p is close to a power of 2, and you can think of them as, you know, chopping up to the nearest power of 2. So these are bit strings that can be encoded in here. You hash by exponentiating u to the h part, v to the m part, and multiplying the result. And all of this is modular arithmetics, is all computed mod p. Finding the collisions is as hard as finding a discrete logarithm between these two values. Why? Because if you have hm and h prime m prime that create a collision in this, then this equation must be true. But then, you know, put h prime on this side and m on this side, u to the difference between h's is the same as v to the difference of m. Also, this is the other difference, right? Like, you know, this one is h minus h prime, and this one is m prime minus m. So the discrete logarithm between u and v is delta m divided by delta h, right? Because if you take u to this power, you get a v. Oh no, sorry, it's vice versa, right? So u to the delta h over delta m, you get a v. Sorry, I messed this up. So this is a discrete logarithm between base v to u. And yeah, I should switch these two. Sorry about that. So why not use this? Okay, instead of say, you know, why? Because this is a compression function. These two inputs are both as big as p, and the output is as big as p, right? So if p is close to you know, say n bits, this is 2n bits and this is n bits. So boom, you have a compression, right? Well, because these block ciphers here is like orders of magnitude faster than any implementation of modular exponentiation we know how to do. Okay, like I mean, the factor is like you know, like 10,000 or a million of difference between the speed of this and the speed of the. Okay, I don't remember what's the factor, but like 1,000 at least. All right. Another counter problem with this is that this would be a funny collision function, because if so, who says that this discrete log between u and v is hard to compute? Well, it is. So discrete logarithm assumption works. We don't know fast algorithms to compute discrete logarithm for random points. So if u and v are chosen truly at random, then collision resistance of this thing would be based on discrete logarithm assumption. U and v are public parameters, so they're part of the description of this function, right? So who picked these U and v? Some designers. Well, but if the people who picked U and v picked them so that they know the discrete logarithm, then clearly for them it doesn't hold. Right, this whole argument doesn't hold. If I pick u and v, I could pick v as a power of u, so I know how to compute discrete logarithm. Nobody else does, but I do. If you know the discrete logarithm, then you not only this argument breaks, you can compute collisions immediately. So this is a kind of a nice exercise. Okay, let's say you know the discrete logarithm. How do you actually now get explicit collision? So that's a struggle in cryptography. If you have the U and V would be called common reference parameters. Parameters that are chosen as an index to a crypto system, an instance of a crypto system, an instance of this collision resistant hash function But whether or not that instance is secure very much depends on who and how created these parameters. And here you have a very clear choice. If the parameters were chosen at random by some trusted process, then the security of this compression is equivalent to discrete logarithm assumption, and we can all be happy with this. But if they were created by a bad guy who picked them knowing the discrete logarithm, then he will cheat in compression. He will be able to easily find collisions, and he will also, these explicit attacks on the collision resistance of little h will translate into collision attacks on Merkle-Damgard that uses this little h. So, and these are very practical issues, okay, in security, because, and political issues also. Who chooses parameters? How shall we trust that the people who know how to analyze these things did not choose the parameters to put some trapdoors in them, so that the people who chose the parameters have an edge over everyone else, right? These trapdoors, in this case, is this discrete logarithm between u and v. That is, you know, right here you have it in a clear, this edge between how we could all rest easy if we could trust the public parameters to be honestly chosen, and how by the same token, if somehow this trust is unjustified, then we should all be very worried. Okay, maybe this is a good time. I had more technical stuff about NMAC, but I think some people joined late, so it's a technical thing. I have a department meeting that was scheduled before this class ends, and it's a quarterly department meeting where like all sorts of stuff is supposed to be discussed, and as a member of the faculty, I should participate. So please forgive me. I will make this lecture a little shorter on that account. Okay, and if you have quick questions, let me know. Otherwise, let's continue. And tomorrow I have also office hours. Let's continue on Piazza. That's what I meant. 1, 2, 3. Okay. Okay. Sorry to rush you. Okay. So see you next time. And don't cancel. Don't cancel office hours. Yes. Yes. No, I won't. Okay. All right. Okay. Talk to you later.